Good morning to everyone, and today we will learn few more aspects in NMR spectroscopy, and we will see couple of symmetry elements. Of course, you know very well symmetry as a part of symmetry and group theory paper in the first semester. Most of you would have studied what is symmetry and how the symmetry actually is going to play the chemical shift values of different magnetically active nuclei, that we will see very briefly. And then we will also study, we'll also try to understand what are the different order spectra. I mean, there are three different order spectra are there. For example, zero order NMR spectrum, first order NMR spectrum, and then second order NMR spectrum. So there are three different type of NMR spectra are there. I mean, basically any given NMR spectrum is classified into one of these three. I mean, it can be a zero order, it can be a first order, it can be a second order, and then followed by there is another something what is referred to as. We'll also study what is the nomenclature of Pople notation and what are the consequences. We'll try to study. Okay. Okay, so today we will learn three major things. One is the symmetry elements, and briefly, and also the different types of NMR spectrum, and also the Pople notation. And then tomorrow we will see a couple of nuclear auras or effect, etc. As I mentioned, that I am going to touch very briefly the symmetry. Symmetry has a lot of importance in NMR spectrum. And then the protons on the other nuclei can be classified as heterotopic, homotopic, enantiotopic, and diastereotopic. There are three different types of. So there are four different type of protons that we can encounter in any given molecule. Okay, so one is a homotopic, other one is a heterotopic, and then diastereotopic, and also enantiotopic things. So these things one has to understand so that we can understand the chemical shift trends of these type of protons. Okay, heterotopic and diastereotopic protons will have different chemical shift values, and then they will also have different coupling constants. Okay, on the other hand, the enantiotopic and then homotopic protons will have identical chemical shift value. Sometimes they may or they may not have identical coupling constant to other nuclei. Okay, so both are totally different. So try to understand that the heterotopic and the diastereotopic protons will have different chemical shifts and coupling constants, whereas the enantiotopic and the homotopic protons will have identical chemical shift values. They necessarily need not to have the identical coupling constants. So, but the question is how one will find out whether a set of protons are homotopic or heterotopic or diastereotopic or maybe the enantiotopic. Well, we can follow the substitution test. The substitution, if you want to check if you want to classify a set of protons, what you can do, you can just replace one of the proton with some other element, and then compare both the structures and see whether they are homotopic or anisotropic or diastereotopic. Okay, so for this, just you have to replace with one of the proton, and then you just compare both the structure and then decide what type of proton it is. We are discussing the homotopic protons. This is a propane molecule. For the sake of clarity, I have written one is projecting towards, one proton is projecting towards us, and then one proton is rare side. I have written just for a small notation. There is nothing. We can write as we wish, as you know, that one of the protons I replace with a phenyl group. Now, and then phenyl group, the other possible structure, the phenyl group can be rare side. Whether the phenyl group is front side or rear side, it doesn't matter. Both the structures A and B listed here are shown in this diagram are both are identical. Therefore, these two protons in the propane are said to be homotopic. Similarly, the anisotropic protons. And then again, I'm taking an example of ethanol. and the ethanol CH2 protons, I am just doing the same substitution test. I am replacing with some phenyl. You can replace with any other thing, what you like it doesn't matter, but I am going to demonstrate with the phenyl group. When I replace the phenyl group, then definitely I will get two different structures. You can notice here, this is a prochiral center, and then when you replace phenyl, when you keep the phenyl rear side and front side, then we will get two different structures, what we call it as a enantiomers. Therefore, the ethanol protons are said to be enantiotopic protons. Okay, and then the diastereotopic protons. Again, the same typical the substitution test we can follow. This is a ether molecule, some ether molecule, and then I am replacing with one of these. Again, you can see here, this is an example of a chiral molecule where there is a CH2 substitution is present. So these two protons are usually said to be diastereotopic protons. Why? Because if you can make this substitution with any other group, then you will get basically diastereotopic protons. Therefore, these two protons are said to be diastereotopic protons, because we are going to get, when we do the substitution test, we are going to get the diastereoisomers. Okay, and then there are several examples for a diastereomer. So this is a kind of diethyl acetal, and again the same thing that we can encounter. We can replace the CH2 group with a deuterium substitution. What we get is G and H, both are different dimension. Both are call it as a diastereomers. And then another example that we have a dibromo cyclopropane group, where there is some kind of substitutions are there, and these two protons in cyclopropane are actually said to be are not diastereotopic. On the other hand, the protons on this CH2Cl, okay, so there is a substitution. This is a cyclopropane ring, and then it has a CH2Cl. There is a substitution, and these CH2 and then these CH2 protons are usually called as a diastereomers because of the diastereomeric nature, whereas these two protons do not, because they do have a kind of a symmetry element. Okay, plane of symmetry is there, therefore we don't call it, if you bisect the molecule like this, it has a symmetry, therefore we don't call it as a these two protons in the which are part of propane ring are not call it as a diastereotopic protons, whereas these two protons are call it as a diastereotopic. Okay, so it is not necessarily all the protons, all the CH2 proton in chiral molecules are basically diastereotopic. This is one example. Okay, this is one example. There is another example, because when you make a substitution effect, what we essentially get identical thing. These two are actually called as a homotopic protons. Okay, because there is a C2 axis. Similarly, these are the examples of heterotopic protons. Okay, so just you have two protons. You take any substituted benzene and then replace the ortho and meta protons. Okay, then you can just think of when you make a substitution with the fluorine, then you definitely get two different structures. Okay, a fluorine which is present meta to the nitro is not same as the fluorine which is present to the ortho is not the same as the meta, right? So the I and J structures are definitely different. Therefore, we call these two protons are heterotopic protons. Okay, so the point I just wanted to convey the message is that the heterotopic protons and diastereotopic proton, homotopic protons, and then enantiotopic protons, all are based on the symmetry element. Okay, so when we make the substitution set, we can classify a set of proton. Two different protons can be classified into any of these four. Now, these protons, heterotopic and diastereotopic protons will have different chemical shift values as well as the different complete constants. On the other hand, the enantiotopic protons as well as the homotopic protons will have the same chemical shift value, but then not necessarily the coupling constant. Okay, there is another symmetry element which I would like to introduce here, that is the magnetic equivalence. This already we have learned what is magnetic equivalence. Maybe we can just try to refresh from our remembrance, or maybe let me ask one of you what is exactly the magnetic equivalence. So let me call Alicia. Are you there? Alicia.
Yes, sir.
Can you tell me what is magnetic equivalence and magnetic inequivalence? Are you going through my lectures? Okay.
Yes, sir.
Tell me, what do you call, when do you call a set of protons are magnetically equivalent, or when do you call a set of protons are magnetically non-equivalent or inequivalent? So, are you going through? I really doubt. If you are going through, you should answer. I asked a definition. I did not ask anything. The number of chemical shift values. Isn't it? I'm asking some definition which we discussed. Divya? Tell me, Divya.
Hello, sir.
Don't remember. You're studying or not?
I'm studying, sir,
Then,
but I did not remember.
okay. You have to study properly, otherwise very difficult to follow these things. Fine. So magnetic equivalence means that, okay, there are just take any two protons in a given molecule and then see their respective coupling constant with the third proton in the same molecule. I have given example with regard to the para-substituted benzene, disubstituted benzene, where the substitutions are present in the 1,4 position, right? You can take the protons, any two protons, and then their coupling with the third protons will be totally different. If that is so, then these two protons are said to be the magnetically non-equivalent. If their coupling is same with respect to the third proton, then we say it is a magnetically equivalent proton. Okay, so this is another element in the NMR spectroscopy. So magnetic equivalence and non-equivalence is based on the coupling nature, how strongly or how weakly that it is coupling with the third one is actually determines uh, the chemical shift value, and and then that will basically determine the complexity or simplicity of the NMR spectrum. So just to remember this and study more on this. Okay, there are several examples we have studied, but if you want, you can just go through some of the example. Again, I have given here. This is a cyclopropane, that these two protons HA and the HA. The HA, these two protons, the coupling with this one and this one, if they are same, we say it is HA, and these two protons are equivalent. Okay, but in this case, you can just think of the coupling, the coupling of JAX, okay, JAX and JAX. So both are same. So therefore, we say it is a magnetically equivalent. But in this case, for example, this type of molecule, it is again a cyclopropane ring, but substituted with some other substituents. And if you try to calculate the JAX, is not equivalent to the JAX dash. That means JAX, these two couplings with respect to these two couplings is not same as the JAX dash. That is this one, and then X dash is where it is not shown here, but then X dash is obviously this one. Okay, if this is X, then it is X dash. So this coupling will be totally different. So these two protons, if the coupling is, but then their chemical shift values will be same. Please remember that, whether it is a magnetically equivalent or non-equivalent. So in the those protons will have the criteria for magnetic equivalence is that first they should have the same chemical shift value. Okay, and then second criteria is that they should have same. In order to say those two protons are magnetically equivalent, their coupling to the third proton should be same. Only then we call it as an equivalent. Otherwise, we call it as non-equivalent. Okay, so then these two protons will have same chemical shift values, but then when you calculate the coupling constant, those will be different. Okay, so that's the point. And then again that alene molecules, and then double bond protons, aniline protons. So these are all several examples that we have studied in those cases. Okay, so coupling, just remember these 2 points, that coupling between symmetry equivalent but magnetically inequivalent nuclei typically will affect the appearance of the spectrum. In fact, it is the coupling between the equivalent nuclei that is responsible for the complexity of the spectra of any given system, any given spin system. And then the second point is that the coupling between magnetically equivalent nuclei does not affect the NMR spectrum. Okay, only the inequivalent protons will actually create a complexity, will actually invite some kind of complexity in the spectrum. Therefore, we will be having some trouble in interpreting this structure. If it is equivalent, there is no problem at all. Such a nuclei will give very simple resonance peaks as as per the first order spectrum. So, and their intensities, everything will be followed. So we can easily interpret. But if the two nuclei are magnetically non-equivalent or inequivalent, then only the problem comes. Okay, so these symmetry elements may invite some kind of complexity into the spectrum. So that's the story of the symmetry. Then let us go to the second topic for today's lecture, that is the different order of spectra. So what do you call, when do you call a spectrum, NMR spectrum, as a first order spectrum? So I call a spectrum as a first order NMR spectrum when they fall, when that particular spectrum follows certain rules or certain criteria. And some of the major rules are basically listed in this transparency. You can just see that. So the chemical shift, okay, if you want to call a NMR spectrum as the first order spectrum, then actually you take any two interacting nuclei in the system, and if the chemical shift values are far apart, okay, if the chemical shift values are far apart, and if their coupling constants are far, than the coupling constant, then we say it is the first order spectrum. Okay, and the chemical shift difference, just imagine that difference. What I am talking about, that I have two NMR peaks in two different positions in the NMR spectrum, and this is what I am talking about. In this case, they are very close. In this case, they are somewhat far. In this case, they are even far, right? This is what I'm talking about. The difference between the two spectral NMR peaks, if it is much larger than the coupling, their individual coupling, then we say it is a first order spectrum. Okay, so that is the basic criteria of differentiating a spectrum, whether it is a first order or zero order or second order. Okay, so it should be, the difference should be quite large as compared to the individual coupling constant J. Coupling constant J should be less as compared to the delta mu. Okay, that is what I mean. So all And then with regard quantitatively, and this is how I define that. So this is delta. Okay, this is the difference actually. So it is the resonance frequency, the difference I'm talking about, delta delta in ppm. That means basically the chemical shift value difference between the two peaks. If it is much larger than the coupling constant, so I call it as a first order spectrum. Okay, and if you want some numbers, and this is what I mean is that, okay, so the difference in chemical shift value must the ratio between the difference in chemical shift divided by the with respect to the coupling constant, if it is greater than 6, then we call it as it is a first order spectrum. So essentially this is nothing but we are saying what I said in words. It is a quantitative numbers. Okay, if the difference is quite large, obviously the ratio will be quite large. Okay, and if the j is less, then again obviously this it will be again greater than 6. Okay, so this has to be high and this has to be low. So the numerator has to be higher as much as is possible. Okay, and then j has to be smaller as much as is possible. Only then the ratio when you take it, it will be much larger than 6. Okay, and then some of the textbook you may see that this is a reverse trend is saying that, okay, this ratio j to delta is much less than or equal to 0.05. This is the criteria. Some of the textbook you will find it. Again, that is also same. I mean, some of the people will write it in a slightly different way, but essentially the condition is same. Then, when the difference in the resonance difference between the NMR resonance peaks is much larger than the coupling constant, we call it as a first order spectrum. Okay, so that is the basic principle. And then the equivalent, in the case of first order spectrum, equivalent nuclei do not split with each other. Okay, if you say two nuclei are equivalent, then those basically do not split into each other. That is another characteristic of a first order spectrum. And then again, this point we already discussed. Coupling constant decrease in magnitude rapidly with the physical separation. I mean, the coupling constant rarely observed in the case of if you are looking at the coupling between the beyond 4 bonds. Okay, beyond 4 bonds between any nuclei, and moreover, the coupling constants are independent of field strength. Okay, so we can distinguish the multiplets from individual closed space thing. Suppose if you want to distinguish the individual the NMR peak which are very close by increasing the field strength, that is something it is possible. Okay, they are field independent. Coupling constants are field independent, but then so the stretching of the individual peaks can be observed if you go to the higher field strength. Okay, so in the case of the first order spectra, the n+1 rules actually it is obeyed. So the n+1 rule that we have already discussed, what is that? The splitting. Okay, the individual lines we learn from the spin-spin coupling concept that the individual NMR peaks are basically split into many as is possible. That depends upon the number of adjacent magnetically active nuclei. Okay, on the adjacent atoms. Okay, so that is the rule that we have discussed. So n+1 rule is something that it will be followed. If you say it is a first order spectrum, that should follow the n+1 rule. So if it is having 4 nuclei, definitely its NMR signal should be a quintet. If it is having 3, then it should be quartet. If it is having 2 neighbors, then it should be a triplet. So this is what I mean is that the first order spectrum usually obeys the n+1 rule, where n stands for the number of non-equivalent nuclei attached to the neighboring atom. Okay, so that's the another characteristic of the first order NMR spectrum. Another characteristic is that suppose if you have a nuclei which is separated, which is basically associated with the two different type of nuclei, then again the multiplicity n, for example, that if you take that you have a nuclei B, and this nuclei B is associated with coordinated with A on one side, and then C is the number of equivalent protons on the adjacent carbon atom, adjacent atom, then the multiplicity actually will follow this rule, right? Na plus 1 multiplied by Nc plus 1. So this is the spin, this is the multiplicity rule that it will follow. That means that not only it will follow the n plus 1 rule, but if a nuclei is surrounded by more than uh, uh, different groups, it's not one group, but then different type of groups are there, then even then also the splitting pattern we can actually observe accordingly. So that is what the point here. Then the other point is that the relative intensities of those splitted lines will exactly follow the Pascal triangle coefficients, or the coefficients of binomial expansion. Okay, so these are the some of the general rules or typical rules that we will observe in the case of a first order spectrum. Okay, so what are those? If you just recall, the basic difference is that the differences in chemical shifts are much greater than the scalar coupling constants, or scalar spin-spin coupling constant. And quantitatively, and this is represented with this difference, difference in between two NMR peaks, and then the ratio between the difference in NMR peaks divided by the coupling constant is greater than 6. Or if you take the reverse ratio, I mean inverse of that ratio, it is A by delta delta is much less than or equal to 0.05. So that is the quantitative picture. Okay, so those are the basic definitions of the first order spectrum. And then the equivalent nuclei do not split each other. For example, that you have a CH3 proton, and the CH3 proton do not split with each other. Okay, so that is typically true in all proton NMR spectrum. They do not individually, they will not undergo any kind of splitting. So in that case, that we call it as a first order spectrum. But there are cases where they do split. Certain nuclei on the same nuclei will split. For example, you can just think of an example like ClF3. ClF3. Okay, trifluorochlorine, clathrate molecule, and the chlorine, fluorine both are basically magnetically active. And then in that case, you will see a different splitting. Okay, so they are not said to be magnetically equivalent; they are said to be non-equivalent. Okay, and then the first order spectra typically follows the n plus 1 rule. And suppose if we have different sets of protons on the adjacent atoms, accordingly it will split. In the case of, if you have a nuclei with one side Na number of nuclei, on the other side Nc number of different type of nuclei, then the overall its splitting will be followed by Na plus 1 multiplied by Nc plus 1. And the other thing is that another important aspect of first order spectrum is that it will follow the Pascal triangle. I mean, the intensity ratios that we can basically look at the Pascal triangle thing, and then we can, or else the coefficients of binomial expansion. Okay. Then what do you call the zero order spectrum or second order spectrum? Zero order spectrum is the spectrum which doesn't split at all. This is something that I pointed out at the beginning of my introductory lectures. In the older days, the magnetic which is used in the NMR spectrometer is very, very weak. It is a static magnet. It is not a electromagnet, unlike these days that we come across a very, very huge electromagnet. And then there are certain elements which basically rare earth elements, or the alloys of rare earth elements. They actually, when you subject them to a lower temperature, typically at 4 Kelvin or so, they actually exhibit the supermagnetism, right? When you lower the temperature, they exhibit this supermagnetism. That's how the magnetism works in the modern NMR instrument. But in the older days, when it is developed, people have used a small, static magnet, which we have used, bar magnet. We all might have used. Even now, also, we are very fond of to uh, play with the magnets, right? So those static magnets are kept in the instrument, a very huge one. Okay. So those spectrum, since the magnetic field strength is not very high or is not very intense, then usually what happens, the individual NMR peaks do not split with each other. You may recall in my beginning lecture, introductory lecture or so, I have shown the ethanol spectrum. And the ethanol spectrum, what we expect is that the splitting, modern NMR spectrum will have a lot of splitting. But then those days, and perhaps it is one of the first molecule where its NMR spectrum was recorded, where you do not see any the splitting. It will just show three peaks. One correspond to the CH2, one correspond to the OH, and one correspond to the methyl bond. Right. So that such a spectrum, what we call it as a zero order spectrum, a NMR spectrum, which doesn't show any splitting pattern, we call it as a zero order spectrum. That is the definition of a zero order. Then what about second order? Second order spectrum is the one actually does not follow the first order spectrum. Okay. If the definition, basically, if the in the case of first order, what we said was actually if the difference in chemical shift between the two lines is much greater than the coupling constant, then we call it as a, it is a first order, right? Then the reverse is basically is the definition of a second order. If the difference in chemical shift value of two different nuclei, if it is less than if it is on par with the coupling constant, then we say it is a second order spectrum. And quantitatively, this ratio. So previously we said it was actually, it is, if it is greater than this ratio, if it is greater than 6, then we call it as a first order. And then if it is less than 6, then we call it as a the second order. Okay. The reverse ratio, when you talk about, then it should be actually J, the ratio of J divided by the delta delta is much greater than 0.1. If it is so, then we call such a spectrum as the second order spectrum. And that in the case of second order spectrum, we normally don't find any kind of the splitting pattern as expected from the n+1 rule. Okay. So what are the rules that are governed a first order spectrum do not apply here. What are the first rule that, okay, if it is the first order spectrum, it will follow n+1 rule, where n is the non-equivalent protons, non-equivalent protons and the adjacent atom, right? So that rule will not apply here. It will show something else. Okay. And then there is another typical nature, and then most of the cases we encounter is that in the case of if the difference is reducing and if it is approaching the value of the coupling constant, then what happens, the individual lines becomes, they will try to tend each other, right? Suppose I have the two NMR peaks over here, and imagine I cannot show the splitting with my two fingers, but then imagine these two NMR peaks are having coupling. They are having basically they are splitted into, maybe let's say it is a doublet. Okay, so this line is two line, this line is two. Okay, so what do I mean by this second order spectrum? This difference is much on par with this I mean the splitting constant, right? In that case they will be very close, right? So when they are closing each other, and if the difference is reducing and if it is closing with the coupling constant, they will come like this. Okay. And please remember that they have inner lines and then outer lines. Two, this line is 2, this line is 2, and then the total 4 lines are there. And then the 1, 2, 3 if you label, and then 1 and 4 lines basically will try to reduce their intensity, while the inner lines will try to enhance, will try to increase their intensity. So that's the typical nature of any second order spectrum. I just explained with an example of doublet, two doublets, but then you can explain with anything. Okay, you have a doublet and triplet, and if the coupling constant is basically is matching with the difference in chemical shift value, then these doublet and triple will merge with each other. In all these cases, what happens is that the inner line intensity basically goes up at the expense of the outer line intensity. So that is the typical nature of a doublet, typical nature of a second order spectrum. Okay. However, the second order effects we can actually simplify by recording the same NMR spectrum with a much higher and the higher field magnetic spectrometer. Okay, what I mean is that in a given instrument, a given molecule may show a second order effect, but then it can be simplified. For example, uh, you recorded some organic molecule in a 200 megahertz NMR spectrometer, and then where this molecule showed a second order effects where these lines are basically split with each other, and then you really don't see any clarity and to interpret the protons. But then the same spectrum, same molecule, what you can do in order to see the first order effects, so maybe you can increase the field strength of the spectrometer. That means, uh, of course, you have to record a different instrument. You cannot do in the same instrument. What you do, you just the same molecule, you give it to another instrument where it is available, maybe 400 or 500 or 600 and so on. Then what happens that these secondary effects what we have observed in the lower frequency spectrometer will no longer will be seen in the higher frequency magnetic spectrometer, because as the field strength increases, the separation between the individual peaks gets increased, and then we can see nice clarity, and then the second order effects will be minimized, and then we can see a better we can see a much simpler spectrum, which will actually allow us to interpret the peaks in a better way and in a easy way. Okay, so that's the definition of or the couple of points about the second order spectrum. And then after this, we can go on to the next topic, that is the Pople nomenclature of coupled spin systems.
When any unknown spectra is given to me, then that time I don't know that which signal is responsible for which hydrogen atom. Then how I can calculate the mu by J value, or it will be given?
See, this is basically, you will be given, mu is given, no? The spectrum scale is there, right? So you can just see any two peaks which are adjacent, and just measure their difference and their splitting pattern, the difference between the individual lines also you can measure, and then you can calculate the uh, value mu by delta by J, you can calculate.
So
So what's the problem there?
J values will be given for individual signals.
Yeah, J value is applicable only if you come across a singlet, it is not applicable. What J refers indicates, J refers to the splitting, right? Spin splitting constant. How strongly, how weakly they are coupled with each other. That is the parameter, that is the information that we get from J value. Okay, if it is J is strong, higher value, then we say it is basically strongly coupled. If J is less, we say it is a weakly coupled. Strongly coupled, weakly coupled. And there are cases where it doesn't show any kind of splitting pattern, which means that they don't couple, right? For example, you have methyl proton, which is not having any neighboring proton. So definitely it will show a singlet. It will not show any splitting. So this is not applicable for that. If everything is singlet, then there is no discussion of what we are discussing. First order, second order, there is nothing. The discussion is only applicable when you have a splitting pattern. Okay, when you have a splitting pattern, then what happens? In certain cases, the lines will merge with each other. Okay, so that invites a lot of complexity in the spectrum while interpreting the data. So to answer your question, that you have a spectrum. If you have a spectrum, that means you know the scale on the x-axis, then just the what point a particular peak is there, okay, and it is also possible you can also find out what is the other value for the other NMR peak, and then the difference is something that you can easily calculate. Okay, that is the delta. Okay, now then you concentrate on only one peak, either left side or right side peak, and then see the splitting. If they are splitting, right? So what is the difference between those two splitted lines? That you just try to calculate. Okay, that is J, right? We discussed already this point. That is J. This J and this delta, the difference you compare, and you take the ratio. Then you can calculate the delta by J value. If it is 6, then it is said to be first order spectrum. Of course, if you are really working with regularly, that you can easily say a particular feature is a first order feature or second order feature, that you can say. That's not at all a big issue in calculating that ratio. Just you have to know, as I told you, that you have to know for calculating J, you have to know the field frequency of the operating field NMR spectrometer. It is a 200 megahertz or 300, 400, etc. So that you have to know, and then you take the difference and then multiply with the frequency of the instrument. That will give you coupling constant J in hertz. Okay.
Okay, sir.
Is it clear? Okay. Okay. We will continue the nomenclature of Pople notation. Well, the Pople nomenclature is very common in NMR spectroscopy. And fine, this Pople is one of the nice theoretical chemist. He has proposed and he has done a lot of work in the field of theoretical chemistry and computational chemistry, and he has given a nomenclature and for the different spin systems in the NMR spectroscopy. And the spin systems, each set of chemically equivalent spin system, what he proposed is very simple. Each set of chemically equivalent protons are designated with the letter of alphabet. That's the nomenclature of Pople. Okay, and this is really this type of assigning the equivalent protons with the letter, with the alphabet letter, is really helpful in uh, understanding and analyzing the complex NMR spectral patterns. Okay. How it works is very simple. That okay, you have a one type of proton. Okay, this type of proton, and then of course in a given molecule, we will not have only one type of proton always, but then most of the cases we come across more than one type of protons are there. So depending upon the chemical shift values of these individual nuclei, magnetically active nuclei, we label them with different alphabets in the alphabets, different letters in the alphabets. For example, I have a peak, and I do have another peak, and if they are basically well separated, okay, what I mean is that Pople is proposed like this. Okay, if they are well separated, then I label one with A, other with B. Okay, A and X. You just recall in the alphabet, A is the starting letter, X, Y, Z. Okay, so almost in the ending position, we will come across the X, right? That means it indicates that these two peaks are well separated, right? So such a system, such a molecule, we represent with AX. Okay, it can be different molecules, but then it comes under one category. What is that category? It is a AX system. AX system, spin system. So what is A and what is X? A and X are two different chemical shift values, or two different type of proton, or two different type of carbons, or maybe two different type of fluorines. It depends upon what kind of NMR that you are really performing. Okay, so A and X are and basically in the alphabet they are very far apart. Likewise, in the NMR spectrum, these two protons, any two protons have well separated chemical shift values, then we call such a system as a uh, uh, the AX spin system. On the other hand, and you can have a different varieties of spin systems. Other one is AMX, what I'm calling as a AMX. And if you see that M comes almost at the middle. Okay, so again, in between these two, you can have another line. But then still, if you are able to distinguish one from the other, and if you are able to assign the task, that's all fine. But then this is another type of notation. And then we also come across different variety of spin system: AB, ABC, MN, XYZ, A3, X3, AA dash, BB dash, okay, A2, X2, AX3. So these are variety of spin patterns or uh, spin system that we can come across when we are studying the NMR spectrum. So that is the nomenclature of Pople notations. Are you following? So Pople notation is very simple, that a set of chemically equivalent protons are basically represented with a letter of alphabet. Okay, and if they are close by, then we represent with a closely separated values like AB. AB are adjacent, right? If NMR peaks are very close by, then we label them with AB. And if you have a three peaks which are close by, then we label with the basically ABC, right? Likewise, and if they are far apart, AX. Okay, you have three peaks which are basically nicely, reasonably separated, then we represent with AMX. So this is the notation suggested by Pople. Okay, so when we come across, when you study NMR, a spectrum of different variety of molecule, all those things are basically classified into these different spin systems. So I'll quickly show some of the spin system that we come across and their examples also. I will show you. That will be helpful when we are interpreting the NMR spectral lines. So AX system, as I told you already, that the chemical shift values will be well separated. So there is no doubt at all. The chemical shift values of the AX system is well separated, and then it will be definitely a first order spectrum, and definitely it will be a first order spectrum, and then there will be two doublets also, right? Because A is basically looking at the is basically feeling the vicinity of the X, and then X is feeling the vicinity of the A. Therefore, both will split into two doublets. Okay, this doublet refers to the A, this doublet refers to the X. So these are the examples of AX system. Okay, so this trans protons and then cis protons can be basically classified as a AX system. Okay, another example is AB system. AB system, the example is this. Okay, this is the example. What is A and what is B? So this is one set of proton and this is one set of protons. And here the proton is coupled to CW1O. Here it is also CW1O, but then on the adjacent carbon it has a COO2 ester group, and this is also ester group. But in this case, the proton is attached only to one this thing, right? And when you look at the chemical shift values between this and this, it will be almost very close. Okay, because here you have two ester groups. These protons have the vicinity of two ester groups, but here it has one ester and one alcohol group. So more or less, both these set of equivalent protons will resonate nearly adjacent, nearly close by. Therefore, we classify this molecule as a AB system, and then AB system, A is interacting with the B and B is interacting with the A. So there is a mutual interaction, mutual coupling. Therefore, we don't see the actual doublet which we normally encounter in the case of AX system. Please remember that two spins means that A and X, A is one spin, the X is another spin. Here also, A is one spin, B is another spin. So both are basically feeling with each other. So in this case, both are basically seen at two distinct locations, whereas in this case, both will still show a doublet, but then those doublet will be coupled with each other, and then we don't see actual doublet, but instead what we see is a kind of quartet. So this is a doublet of a doublet. You can see here, this is something characteristic that I have already explained to you in the case of second order spectrum, where in the case of second order spectrum, as the separation basically decreases, and what happens as the separation between the NMR peaks get reduced, accordingly that inner lines basically intensity reduces, while the inner lines intensity goes up at the expense of the outer line. This is the point I made it. Now this is a true example of that. You can see here, initially that these will be like this, very far apart. But then if this difference is decreasing, if this difference is decreasing, then we call AX becomes AB, right? AX become AB if this difference, what we call as a delta, okay? The difference, if this is decreasing, then what happens? These are called outer lines. This outer line intensity goes down at the expense of while the inner line intensity goes up. This is what exactly happens, and then it will turn to this type of spectrum. Okay, so these are the two examples of a compound, and likewise we have.
Sir,
Yes, Kuntal, please tell me.
sir, in case of AX system, there was neighboring hydrogen, but in AB there was no actual neighboring hydrogen. Then why they are splitting in doublet?
Oh, so I think let me verify this. I'm not sure whether I copied the right example or not, but then to answer your question, probably this is the reason, or this ethyl protons. I have to check basically. So here there is a ethyl group. So these AB protons are these ethyl group, or a different one. Let me verify. It's a good point. What you raised is a good point. I did not check this one. Let me check the textbook. Okay. I think your points are valid. Yes. If I was discussing only these 2 points, but then they don't have any neighbors here. It is connected with a C, but then the C double bond O here. Then what he is raising is that he is connecting with the 2 protons are here, and these 2 protons do not have any neighboring protons. Okay, so this is having directly a carbon here. So this point is very valid, very much valid. Let me verify. I'll get back to you in the next class whether this is the right example which I copied or there is something different. Okay, is it okay?
Okay, sir.
Okay, I will come back to you next. Then there are several examples of this kind. Uh, Okay, let me check where it is. Fine, fine. I'll come back to it. There are several other examples where we see AX and AB type of spectra, and these are the examples. You can have a disubstituted alkenes of the examples. Okay, this particular system is called as a AX system. As you can see here, it's NMR spectrum. The well separated doublets. So this one is coupling with this one. You have well separated one, whereas this one is having very close by this is germinal protons. This germinal protons are very close by, right? I think I do probably this is what I think what happens. Maybe this is an example of a trans. Usually, I think Kuntal, listen. I think this is an example. So this spectrum, what we see here is a AX system, trans protons. Okay. Probably what I might have done, this example should be here. I think that is the mistake I might have done it.
Okay, sir.
Okay, but I will confirm. Okay, but I will confirm this. Maybe this vicinal, this cis protons coupling. When you just see, okay, this will couple with this, and this will couple with this. So this is a doublet, and this is a doublet. Both will merge together. So probably that is the that becomes a AB system. Like in this case,
Sir,
here
in case
also.
of the C's, it should be far apart according to this iodo compound.
What is that?
Sir, this substituted
That, listen, that is a different thing. This is actually vicinal coupling and then vicinal and germinal. There is a trans and then this one. So both are different and both are different structures also. So don't compare this and this. Okay.
Okay.
These are germinal protons and these are basically vicinal. But the previous molecule, the comparison is between a trans protons will have, these are the trans, no? Trans proton, and this is called vicinal protons. Okay, so this is the difference between this and then the next molecule. Okay, so you can see here the disubstituted alkenes again. You have well separated peaks, doublets. Therefore, this is said to be AX system. This molecule comes under AX. Okay, whereas this molecule it is very close by. Therefore, this is called AB system. Okay, so likewise we can go on discussing. We have different examples are there. This is another tetrasubstituted I mean benzene. And then you have these two protons are nicely far apart because the chemical environment of these two protons are totally different. This is having a acetyl group, whereas this is having a methoxy group. So naturally these protons will have two distinct chemical shift values. Okay, and therefore they come under this will come under AX system. Okay, whereas protons on this molecule or this molecule, as you can see here, the inner lines actually the intensity goes up while the outer line intensity is very very small. The example for this one, these comes under AB system. These are basically the AB system. So the both are AB system. You can see it is like a quadrant. It is not exactly quadrant, but then it is appears to be a quadrant. Okay, so I think these two protons are. What I mean is that these two protons. Okay. I think this is the energy levels of AX and AB systems is something beyond the scope of this course, but then you can always refer the physical chemistry concept. I mean, you can just treat this molecule, you can treat the interaction between the two spin system as a perturbation, and then you can apply the quantum mechanical uh, approach, and that's how the Pope actually has suggested and did a lot of calculation on this. and he arrived at different equations which will actually give a nice explanation or nice way to represent different type of chemical shift values and the center of the chemical shift of a quadrate or maybe a triplet or maybe a doublet of a doublet, etc. I think you need not to worry about these things because this is the beyond of this particular course. Okay, so I will not just discuss this thing, but then the point what I would like to bring to you is that okay, you have a AX system or AB system. How do you represent in the text? The normal, how do you communicate these results when you communicate a research paper? So, how do you basically represent the AX system and the AB system? Or that certain calculations are made and certain things are basically represented. Okay, since if it is not appearing as a actual, it is not a quadrant. So doublet of doublet is not a quadrant actually, but then how do you exactly represent in the NMR spectrum? For that, what is done is that there is a small calculation one can do to represent the to find out the middle of the quadrant. Why it is needed? Why you need to find out the middle of the quadrant, this quadrant or the doublet of a doublet? Because in the NMR, data when you represent, you have to say it is a doublet of a doublet, or these two doublets are merging together, and then they appears to be a quadrant. And this information, when you record the NMR factor, this information you are getting. But how do you say it is a doublet of a doublet? As I told you that we cannot always give the NMR peak, NMR spectrum. It is not really wanted in nowadays, unless it is really a rare molecule which is having a great importance. Normally, nobody show the NMR spectrum. So nowadays, everything is represented in a text format. Right? So how do you actually represent the AB quadrant or a doublet of a doublet or AX system in the given thing? So AX is straightforward, but in the case of AB, it is not a quadrant and it is not a doublet of a doublet. So it is in between. Therefore, we have to find out this difference in the AB. Okay, how do you find the difference? The best way is that you can take the difference of these inner lines and then you can report. But then that will not always be true. Certain cases the coupling will be different. Therefore, I think there is a formula which is suggested by these people. And this is the formula. So square root of mu1 minus mu4 multiplied by mu2 minus mu3 actually gives you the center value, and then the center value has to be produced when you are representing the data, NMR data in the research paper. So that's the exercise it is. So just go through it, you can easily understand that concept. Okay, so solving the ABX pattern, all those things are basically comes under these two slides. Okay, so there is another method for representing the for finding out the middle of the this quadrant. Okay, which is appearing as a quadrant, so that this graphical method also can be done. For example, that you can draw a horizontal line just above the outer line peaks, and then another horizontal line which touching the top of the two inner line peaks, and then you can basically draw a diagonal that basically pass just above the vertical line that touches the middle of these two lines. Okay, so basically this gives you the value of the middle of this quadrant. So that value is something that you have to represent in the NMR spectrum. And these are the examples of different molecules where you come across, you can see this is a real example. You may ask me, sir, this is a graphical thing, right? This is a graphical thing, right? These are all graphically I have drawn something, but then there are real molecules, they give this type of thing. Okay, now the question is, how do you represent this value in the NMR spectral data? How do you do that? Similarly, this value, how do you do that? They are not actually a doublet, right? They are not a doublet. This is not a doublet. This is not a doublet. In fact, they are actually coupled with something else. So that one we represent it differently. That is what this exercise actually describes, that entire exercise. Okay, so how to report AB quartet is very important thing. There are three ways you can actually represent the represent in the NMR research paper. One is uh, treat the pattern as the first order. Okay, uh, if uh, if the both the doublets are far apart, then you can just give the values like this and then represent like this. Okay, so this is, let's say this is a value for A. Okay, let's say that we are dealing with A, and if these two doublets are far apart, then you can give value for A, and then you can say it is a doublet. D stands for doublet, and you say how many protons it is. It is one proton, and what is the coupling constant? The coupling constant is the splitting. The difference between the two fine lines is the difference. That it is this. Then for B, this is the value. Okay, for B, this is the value. 3.79 is for the B value. Okay, and again it is a doublet, and then one proton, and J value is represented, right? So this is the way to represent AB quartet if they are reasonably separated, and especially if this ratio is greater than 4, then we can follow this method. You can represent both the doublets separately. On the other hand, if they are very close by, then the problem comes. The problem comes, and then you can represent two different ways. One is that you can give that AB. This is AB quartet. Okay, this AB quartet value, just give. You find the center of those quartet. How to find the center of the quartet? Then you follow this method, graphical method. Okay, this is the graphical method. Okay, or else you can follow this method, this formula. Okay, square root of mu1 minus mu4 multiplied by v2 minus v3. This you calculate. That basically this delta mu AB is the center position of that AB quadrant. Okay, so that value you can find out, and then you can place that thing and then write it like AB quadrant. Q stands for the quadrant, and then you can just write it like it is for two protons, and the delta, the difference, between the quadrants is, whatever it is that you just represent. Okay, and then the coupling constant also you can represent. Another way is that you can represent, instead of representing only one, you can also represent the two doublets separately. That is also possible. So there are three different ways when we are representing the NMR data in a research paper can be followed, and so this is more appropriate. These two positions are the more appropriate way to represent the data, AB quartet. This is not the method it is followed. So that these two methods are the correct method to represent the AB quartet. This method is okay only when AB type of the chemical shift values are somewhat far apart. Then when you go to the three spin systems, so what we discussed is AB and AX are basically two spin system where A is 1 and then X is 1, so two are there. But then here onwards we have three, we can have three different spins. AX3 is one three spin system where A is basically having two neighbors, and whose chemical shift values are very entirely distinct from its chemical shift value. So that one is AX2 system. So we can have different examples. One is this type of molecule. For example, you have a 112 trichloroethane molecule is there, right? So here you have one proton, okay, and whereas here you have two protons, okay. these two protons, the coupling, this you can call it as a A, and this you can call it as a X. This is X, and then this is another X. So AX2 system. This is an example of AX2 system, and whose NMR spectrum will be a first order spectrum. Absolutely no problem. That A couples with this proton and this proton in the same manner. Therefore, the coupling will be same. Okay. And when you record the NMR spectrum, then what you come across is that A is split into a triplet because it has two neighbors. On the other hand, this X split into a doublet. Okay, so these are the two different peaks that we encounter in the NMR spectrum. Okay, this stands for A because A is having two neighbors. Now, on the neighboring atom, it has two. In this case, it has two. The X case, it has only one neighbor, that is only one A is there. A is also half split, so it will split into a doublet. And similarly, we can also have the AB2 system. Similarly, we can also have AB2 system where the chemical shift values of one signal can be very close to the two chemical shift values. Okay, two signals. Then this is an example, pictorial representation of these two, and this is how it will look. And the best examples are the tri-substituted benzenes are the best example for AB2 systems. Okay, and this is a conversion. Of course, AX2 can, like AX can convert into AB2 if the difference in the chemical shift value is matching with the J. Likewise, if the difference in A and X2 system is decreasing, then this will make a transition to AB. This will become a AB2 spin system. Okay, so how these peaks will transform into a new one that we can basically encounter. Okay, so this is entirely different case. This is the AX2 system. But as you can see, if this ratio is decreasing, okay, if it is becoming 5, if it is becoming 2, if it is becoming 1, how you just monitor how these what is the nature of these spectral lines. Okay, so these outer lines, as you can see here, that outer lines will goes down while the inner line intensity goes up. So this is the these are the examples of AX2 and the AB2. Similarly, we can also have the AMX, ABX, ABC systems, and these are the example for those. So this is an example for AMX system. This you can think of A and then M and X. Okay, so this AMX system will have reasonably separated spectral features. Therefore, it will be a first order spectrum. AMX system, NMR spectrum, when you just monitor, then it will be a first order spectrum. Whereas the ABX and the ABC will be a second order spectrum, and their typical nature is shown here. So AB will split into as many based on the number of these things. Okay, this will be, so you cannot expect the same number of the lines what you expect in the case of first order. You can just remember that it has how many X is, this is the X line. X is having two neighbors. One is B and one is X, right? There are two. If it is 2, according to n plus 1 round, then it should be, you should see a triplet, but then you can see a 4. You are seeing 4 lines. So this is the typical nature of a second order spectrum. Okay, it will not follow the n plus 1 rule. That is what I was telling in the beginning of the first order, second order definitions. Okay, likewise AB. Okay, this is for AB also. You will see so many lines, and then you just, this is an example of ABC and spectrum, how complicated it is. If it is simple order, then you don't see these many lines, right? You have many lines here, and these are the examples of real examples of those molecules. And then when you go to the 4-spin systems, like this is the best example for 4-spin system where it has this particular proton will have how many three neighboring protons. Therefore, it will be a first order spectrum, and then you can easily interpret the spectral features. And again, when it goes to AB3 system, so this is again for spin system. It is a second order, and A2X2 also is possible. When you come across the 4-spin system, A2X2 also possible, where you have two equivalent protons will have a adjacent two equivalent protons. That is also 4-spin system. Again, A2X2 system again comes under first order spectrum, where you can see nice distinct peaks. Then corresponding the triplets can be easily interpreted. Again, A to B2 becomes, which is very rare molecule, but then this spectral feature will be very complicated as usual. Okay. Similarly, we can have AA dash XX dash. For example, this para-substituted benzene rings are the best example for AA dash and XX dash. Okay, so whenever you encounter this kind of molecules, then the coupling constant will be different. Okay, coupling constant of these two protons. Okay, with this coupling will not be same as this coupling, right? So that's what we call it as a magnetically non-equivalent protons. So likewise, we can keep on discussing different spin system. Different examples are here. You can just go through it. So wherever the alphabets are far apart, if you are showing representing the spin system with little far apart alphabets, then we say it is fairly easy to understand such NMR spectrum and easy to interpret the NMR spectrum. Whereas when you start representing a particular NMR spectrum with the alphabet letterings which are very close by, such a system is very difficult to understand the NMR spectrum. Therefore, such a system actually is requires much more attention to interpret, where probably you can think of recording the same NMR spectrum in the higher field NMR spectrometer, which probably will help us to resolve peaks like this. For example, this is a 5-spin system. There is a 5-spin system where you can see a nice separation. This close by these spectral lines are very close by, but if you can go to higher field NMR spectrometer, then you can see a nice separation. Okay, this is all for today. And today, mostly I have discussed 3 parts. One is very briefly how the symmetry basically will affect the chemical shift values, and also the Pople notation, and also what else? The other point. Symmetry elements, and then first order, what are the rules that govern the first order, second order, zero order. Then the last topic, Pople notation, and how the representation of different molecules using different spin system by the Pople notation that we have discussed. So with this, I finish today's lecture, and if you have anything, maybe we can discuss any doubts or any clarifications. Otherwise, we can meet tomorrow morning again. Okay, if you have any doubts, probably you can keep it. Maybe tomorrow we can discuss. Okay.